Swayam Prabha. Digital India. Educated India.
Well, a very good morning to all of you. So, we have assembled here to study the fundamentals of multiphase flow, and I begin with an assumption that you have already covered the basics of fluid flow, at least you know what happens when water or air flows through a particular pipe. So, that now you can appreciate what happens when both water and air are introduced in the same particular pipe, how the characteristics of flow change, how the hydrodynamics change, and how to quantify and how to estimate those changes. So, these are the things that I would be covering in this particular subject of multiphase flow. Now, before I start anything, naturally probably you are not very acquainted with this particular subject as you are acquainted with other common subjects like say pollution controlled, nanotechnology. So, these things are maybe biochemical engineering. So, this is a comparatively new concept probably to you. But the first thing which I would like to tell you is that multiphase flow, it prevails in all other subjects that you have come across, like in pollution or say in microfluidics, or say in all the biochemical engineering, in biotechnology. In all these things we usually encounter two or more than two fluids or two or more than two phases flowing together, and we hardly come across situations where only one fluid is flowing. So, to be very honest, multiphase flow is much more prevalent industrially as well as in your daily life as compared to single phase flow situations. So, in this particular class, the first thing which I would like to tell you is, firstly, what is multiphase flow? Where do you encounter multiphase flow? To be more specific, maybe you know a number of applications, but just to summarize the whole situation. And why do you need to study multiphase flow? How is it different from the basic fluid mechanics that you have already studied till now? Okay. So, when we talk of multiphase flow, the reference books of course I will be mentioning at the end of the class. So, when we talk of multiphase flow, it is usually the interacting flow of two or more phases where the interface between the phases is influenced by their motion. Now, just note certain things regarding this particular definition. Now, when we give this particular definition, there are certain words. I do not say it is just the simultaneous flow of two or more phases. Now, whenever we mean phase, it is just the phase which you have studied in thermodynamics. It is that particular state of matter which is continuous throughout in chemical composition and physical structure. So, when we talk of phases, it is either a solid phase, a liquid phase or a gaseous phase. Okay. Now, remember it is just not the simply the presence of two or more phases which guarantees multiphase flow. There are certain words here, the interacting flow of two or more phases, which means that we call it multiphase only when the phases they interact among one another, and as a result of which the interface between the phases is influenced by this motion. A very classical example which I would like to give you is, suppose you have flow through packed column, say water is flowing through a packed column or say air is flowing through a packed column. Is it is it two phase or is it single phase? Any idea? When water is flowing or say air is flowing through a packed bed, do we call the flow two phase or will we call the phase single phase flow situation? We call it a single phase flow situation because in this case the interface between the solid and the air or the solid and the water does not change with the motion, and we find that the interface is not influenced by the motion. Simply the fluids which is flowing, it simply flows between the vortices which are available in this packed solid. Moment we keep on increasing the flow rate, a time comes when the entire thing becomes fluidized. Moment it becomes fluidized, it becomes a two-phase flow situation. So, therefore, remember one thing, simply the presence of two or more phases does not guarantee multi-phase flow situation. It is that particular situation where two or more phases, they interact. The place of interaction is obviously the interface between them. So, we call that particular situation multiphase, where the two or more phases, they interact at the interface, and as a result of this interaction, the interface that changes, and that takes up a large number of forms, and accordingly the study of multiphase proceeds by studying the different forms which the interface can take. Now, we have solid phase, liquid phase, gas phase. So, from these combinations we can have either a two phase flow situation, it can be a solid liquid or it can be either a solid or a solid liquid or a liquid gas or a liquid solid situation. It can also be a liquid liquid situation also, where two immiscible liquids are flowing. We can have three phase flow situations also. For example, oil water gas phase flow in petroleum industries, sand water gas flows in the stowing of mine voids. We can also have a four phase flow, even oil water gas solid, that we can encounter in oil explorations. But the most common feature which we find is the two phase flow situations, where it can either be a gas liquid, liquid solid, solid gas flows, or it can be a liquid liquid flows as well. Now, whenever we talk of such flows, this particular diagram, it shows you the entire range of two phase flow situation. We find that we can have a two phase flow situation for the entire range from gas to liquid. That means, from very low gas, very low gas, a large amount of liquid, to very high gas and a small amount of liquid. Over the entire range we can have the two phase flow situation. On the contrary, for solid, liquid and gas solid phases, we find that more or less when the solid packing becomes much more dense, maybe more than 50% solid loading when we have, then under that condition the interface is not influenced by the motion of the phases, and we have single phase flow situations. So, for liquid solid and gas solid cases, maybe we have a two phase flow situation which is bounded by this particular line and this particular line over a limited range of flow conditions, and for the rest of the situation, just like the packed column which I had said, we have a single phase flow situation. So, there is limited two phase flow for gas solid and liquid solid cases, while for the case of gas liquid cases we have it over the entire range of composition, starting from very low liquid, very high gas, to very high liquid, very low gas. Because this particular flows, you will find that this is most widely studied, probably it is quite complex in the sense. Why it is very complex? Because in this case there are two things, both of them they do not have a particular shape. Just like in solids they have a particular shape, but gases and liquids, none of them they have a particular shape, and therefore they are characterized by a deformable interface combined with the compressibility of the gas phase. So, therefore, what happens in this case? The interface is deformed, and the other cases the gas is a compressible fluid. So, naturally some portion of compressible fluid flow also comes into picture under such circumstances. Therefore, gas liquid flows, they are slightly more complex as compared to, or rather maybe they have a little more variety, I should say, as compared to gas solid, liquid solid flows. And liquid liquid flows, it is a comparatively much more recent topic, and this has come up with the advent of, say, petroleum industries, liquid liquid extraction, chemical reactors, etc., etc. While we find that the other things, the other types of flow, gas liquid flows, they are, as you know, these applications you already know, boiling, condensation, adiabatic flow, whenever they are in power plants, we have such type of flows. Gas solid, it is in pneumatic conveying, combustion of pulverized fuel, flow in cyclone separators, etc. Liquid solid, slurry transportation, at least chemical engineers have come across it, I believe. Food processing, various processes of biotechnology is there in gas liquid, liquid solid, in all such cases, even for liquid cases also. Now, in a nutshell, if I would like to show you the practical applications of different two-phase or multi-phase flow situations. Now, the idea of showing you is just to show you in the variety of industrial cases in which we encounter such type of flows. We find it in power systems, a large number of examples are given, and heat transfer systems, heat exchangers, evaporators, condensers, spray cooling towers, dryers, and so on and so forth. Process systems, almost everywhere you find two-phase flows, in whether it is a distillation column, whether it is liquid extraction, emulsifier, atomizer, scrubber, in everywhere we find process in different process systems we find that several applications of multi-phase flow, or rather multi-phase flow occurs in a large number of applications. Transport systems, definitely in airlift pipeline transportation, very common in oil explorations. Pneumatic conveying, pipeline transport of slurries, we find it. Information system also, superfluidity of liquid helium and the charged liquid films, due to this two-phase flow occurs. Lubrication system, definitely environmental control, as I have said, in air pollution equipments, scrubbers, cyclone separators, most of the cases you find two-phase flow situations to be there. Geometeorological phenomena is there, and of course, if you see the biological systems, your blood, your body fluids, almost nothing is a single phase. Most of them are either emulsion or suspension or something of that sort. Now, when you look at the range of applications, you find at one end you have air water or steam water flows, at the other end you have, say, suspended solid flows, you have slurries and all those things. So, it might occur to you that it is too vast, and how can one particular subject or one particular principle govern all this type of flow phenomena. Now, we will find that in all these types of flow phenomena, what we find is that certain initially what was the attempt, initially the thing which was done is that each and every system was taken up, and the approach was essentially empirical in nature. So, therefore, the study was primarily empirical, and design equations were suggested or operating conditions were suggested based on the system. So, people used to think that whatever is applicable for biological fluids will definitely not be applicable for oil industries. So, therefore, it was of a limited generality. There was another thing also. See, maybe in the early 21st centuries also, under that condition, if we take the power plants, we find that in there mostly the designs were empirical, very low efficiency was there, and a large amount of power or rather large amount of fuel loss was there, and at that time the performance probably was governed by the material constraints. The materials were not very well developed, so the boiler material etc. were the limiting constraints to decide how well the boiler is going to perform. Now, what has happened? Now, we find that under the present circumstances, metallurgy has improved a lot of new materials have come up, and then there is an increased pressure for much better performance, more reliable performance. That is number one. Number two, now safety has become very important. Now, if safety has to become important, you need to know number of things. You need to know the safe operating limits, under which limits you are supposed to operate, and where you should not, in which particular territories you should not invade. Then in that case, you have to know the limit of operations, under what range of conditions you should be operating, and in a less fortunate situation, if there are faults, how to diagnose the faults. In case you have to know these things, you need a good amount of data on the hydrodynamics and the heat transfer characteristics of the two-phase flow situation or the multi-phase flow situation, which is undergoing under that particular conditions. Then if you have, then in that case you need a optimum design. Now, in order to have an optimum design, you need to know the proper design equations, which will again depend upon the fluid flow characteristics. If there is a heat transfer, it will depend upon the heat transfer calculations. You need data on, say, two-phase pressure drop, you need data on heat transfer coefficient for multi-phase flow situations. Okay. So, we find that now and there is certain other things. Now, probably we go for larger scale of plants. Whenever we go for larger scale, we need much more accurate data. Now, and on the other contrary, we have come to microfluidics. So, for flow through micro channels as well as flow through a larger scale, for all these things the physics slightly becomes different. So, unless we understand the physics of multiphase flow, it becomes very difficult to go into areas which have not been studied previously or which were not very prevalent in earlier times. So, now therefore, we find that the incentive to study multiphase flow, that comes from 3 points of view. Firstly, it is the designer's point of view, next it is the operator's point of view, and finally, it is the safety. From designer's point of view, as I have already mentioned, to optimize the design to produce a product which is much more competitive in today's market, we need a quantitative or rather detailed quantitative study of say heat transfer coefficients, two phase pressure drops and things like that. For the operators, they need to know the optimum operating condition, and in a less fortunate situation, they need to diagnose faults which has already occurred due to departure from the ideal condition. So, what we need to do? We need to perform some experimental investigations in a particular geometry, or we need to find out the two phase flow regimes which are prevailing. For example, say suppose a fault has occurred because the flow has become stratified. So, if we just change the flow condition, we will see shortly, and if we can break this stratification, probably we can have a problem free operation. So, those things we need to know. Next, obviously, now safety has become very important. So, for these particular things, the incentive to study the hydrodynamics of multiphase flow, the heat transfer characteristics, that has become very important in modern times. Now, if we have to study, well, this I will come later. Now, if we have to study multiphase flow, then the first thing is, you know now what is multiphase flow. You find out that it is simply the flow, whether it is interacting flow or it is non-interacting flow, it is basically fluid flow. Okay. So, therefore, our analysis should start from the basic equations which governed single phase flow in different conduits. We should start from there itself. Now, for analyzing such fluid flow, what do? We write down the equation of continuity, equation of momentum, equation of energy. Then we have several constitutive relations, boundary conditions, certain constraints. We apply those and try to solve these equations. Definitely for multiphase flow, we should approach in the same particular way, and we should first write down the equation of continuity, momentum, energy, and then we would like to solve them. Maybe the constitutive relations will be slightly difficult or different for this particular case. Why? Because in single phase flow, the fluid is interacting only with the pipe wall. In this particular case, what happens? The two fluids, they interact separately with the pipe wall, but at the same time they interact with one another as well. So, let us first derive the momentum equation, the equation of momentum, the equation of continuity for single phase fluid, and then we will see how that equation, just we will be taking up case by case and doing it with much more details later. Just at first glance, how that equation should change for multiphase flow, and in order to use the changed equation, what are the things that we require. Okay. So, suppose we take up simply say water flowing through a closed conduit, say which is inclined at an angle theta with the horizontal. Now, in this particular case, we say this is the direction of flow. Now, this particular length, it is a small length, say delta z. Now, in this particular case, I think I should draw a slightly bigger one, that will be easier for you to understand. This is delta z, say the cross sectional area is say A, and your interfacial area, it is say S, the interfacial area. Okay. So, the direction of flow is this. Now, if this is the direction of flow, then in that case the pressure force will be applied here, it is P A here, and in this particular case it is going to be P plus. Any doubts anywhere, you can just stop me and you can ask me. This becomes area. Okay. Wall shear stress, this you already know, it is just a recapitulation for your convenience, and then definitely there is a gravity force also which is acting in this particular direction, say F g is the gravitational force acting. Interfacial area is S. Okay. S we have taken as the interfacial, it is just the wetted area, the perimeter in this particular case, it is just the perimeter, the area in which the shear stress applies. Where does the shear happen? The shear happens at the wall. Okay. So, therefore, where does shear happen? It happens around the entire circumference of the wall. So, therefore, the shear stress multiplied by the entire circumferential area, that is the wetted perimeter area in this particular case. Now, for this particular case, suppose we write the equation of continuity. So, this gives you W equals to rho into U into A, where rho is the density of the fluid, U is the velocity, and A is the cross sectional area. Now, if we strike a momentum balance or rather force balance in this particular case, what we get? We get integral P minus P plus del P del Z delta Z. If we assume that the area is not constant, then we take it as dA. This is equal to integral over S. This was integral over area. So, this is tau W delta Z ds plus integral over area del Z of GU delta Z dA plus integral over area rho g sin theta delta Z dA. So, we find that in this particular case we are having the pressure force, we are having the wall shear stress or the shear stress forces, and we have the gravitational forces, and as a resultant of this we find this is the rate of change of momentum of the fluid. Okay. So, taking the directions into consideration, assuming that the direction of flow is the positive direction, we can write it down in this particular manner. Now, for one dimensional analysis, suppose usually we have one dimensional assumptions. So, for one dimensional assumption, how does the equation change? Under this condition, we find that all the things they change along the flow direction, and normal to the flow direction it is constant. So, in this case we get P minus for one directional assumption, sorry, not dimensional, one directional unidirectional assumption, we get P plus del P del Z delta Z into A. This will be tau W S delta Z plus d d Z of G U into delta Z into A plus rho g sin theta delta Z into A. Okay. So, this is the thing which we get. Now, in this particular case we find that dividing throughout by or rather if we just solve it, we get minus A dP dz. This will be equal to tau W S dividing throughout by delta Z and taking the limit as delta Z tends to 0. Okay. Should I write it down? Dividing throughout by delta Z. These things you already know, you have done these things several times, but anyhow, and taking the limit as delta Z tends to 0, we get minus A dP dz. This is equal to tau W S plus A d dz of any doubts you can get it clarified from me plus
mass by area.
Acha, one thing I will just mention, this particular term probably you have not come across in single phase flow, it is basically the mass flux. We will be using it quite frequently in this particular case. It is just if we take the mass flow rate as W, usually we are used to taking it as m dot, but in our case I will prefer to take it as W, why you will understand later. Then in that case G equals to the mass flux of that particular fluid. Okay. So, here instead of W by A I have taken it as G in this particular case. Now, so therefore, we find that dividing throughout by A, we find the expression of pressure gradient which we get, that is minus dP dz, that is equal to tau W S by A plus d dz G u plus rho g sin theta. Agreed? This particular definition probably you have come across earlier as well. Okay. So, this is the thing which I have already written it down here. So, where we find that more or less whenever you have been solving, you have found out that for horizontal pipes just this particular term which you call as the frictional pressure gradient was prevalent. When we go to vertical pipes, we find along with frictional pressure gradient, we have a gravitational pressure gradient, is not it? So, usually since for vertical pipes the gravitational pressure gradient is much less as compared to, the frictional pressure gradient is much less as compared to gravitational component. So, usually for vertical pipes we just used to say that minus dP dz equals to rho g sin theta. Okay. But definitely there is a frictional component as well in under that condition. What probably you have not come across much is this particular pressure gradient. Any idea of what this particular pressure gradient it signifies? Change in velocity and mass flux. So, it is the acceleration pressure gradient. Okay. So, we find that the pressure gradient it comprises basically of three components. It is the frictional pressure gradient and the acceleration pressure gradient as well as the gravitational pressure gradient. Certain things are important under certain conditions. For example, in horizontal pipes this one goes away, in vertical pipes usually this one is much more important, and so on and so forth. Now, acceleration pressure gradient under normal circumstances the fluid does not accelerate, we do not get it. We get acceleration pressure gradient under certain conditions. Any idea under what conditions the acceleration pressure gradient is encountered? Very correct. In case of nozzles and diffusers, we can have acceleration pressure gradient. Why? What accelerates the, rather what causes the acceleration pressure gradient for the case of nozzles and diffusers? The change in cross sectional area is definitely one. Under any other circumstance, we can have this particular pressure gradient. Other than that, under any other condition we can have it. We can have it when, say there is when we have compressible flows, when the density is changing with length, or when there is a change of phase. Okay. Whenever there is something which brings about acceleration, we have the acceleration pressure gradient. Okay. So, therefore, usually this particular component, the acceleration pressure gradient, this is much more important for compressible flows. Okay. So, for compressible flows, what is the situation? We will derive it and then I will show you the actual derivation. So, we find that normally under normal circumstances we do not have this pressure gradient. Probably you have, I do not think you have come across this in your undergraduate classes, but definitely it should have been there, and then you should have cut it out unless there is a change in area or a change in phase or the flow is compressible, and without, if these things are not there, then usually this is cut out. Okay. So, this should be there. Now, this pressure gradient is nothing but d dz of G u, where we find what is this u? This u is nothing but G by rho or in other words this u is nothing but W by rho A. To make it more general, to include all sorts of variations. So, we find that the total mass or that the mass flow rate remains constant. What can change? In order to bring about a change in velocity, either the density can change or the cross sectional area can change. So, therefore, this can be written down as d dz of W can be taken out 1 by rho A, or in other words this can be written as d dz of rho is density. So, what is the reciprocal of density? Specific volume. So, therefore, it can be written down as d dz of V by A. Okay. Now, this can next be written down as, so therefore, it is G W by A. If you take up the entire thing, if it, sorry, I have to take out G out, no, this is all right. And so, therefore, if we take out G here and we deal just with U, so then it becomes G W by A dV dz minus G W V by A square dA dz, which can then be written down as G square dV dz minus G square by A V dA dz, isn't it? Now, tell me one thing, dA dz is fine, you know the change in area with the change in the distance and you can find it out. Now, why does the specific volume change with the distance? Why does this dV dz happen? This dV dz happens just because the specific volume or the density changes with the axial distance z, isn't it? So, therefore, instead of this dV dz, we can write it down as dV dz is nothing but dV dP into dP dz, yes or no? So, this can be substituted in the acceleration expression that I have put up here, and then this finally this acceleration expression can be substituted in the total pressure gradient equation that I have written down or that I have derived, in other words. So, if we write it down, then in that case what do we get? If we write it down, then finally we get minus dP dz, this is equal to tau W S by A plus rho g sin theta dA dz plus g square dV dP dP dz, isn't it? Or if we bring this particular term on the left hand side, we get minus dP dz, this will be equal to tau W S by A plus rho g sin theta minus g square V by A dA dz divided by 1 plus g square dV dP. This is the thing which we get. Okay? And as we go to further, we can find out that what is this, but how can this g and this dV dP, they can be represented, and finally, we can get it here. This entire thing has been done in this particular case for compressible flows. Just whatever I have done, I have just written it down, so that you can see that finally from this particular denominator, we find that this denominator we will be doing compressible flows a little later. So, I will be during that time I will be covering this portion, but for the time being you can very well see that this denominator corresponds to something like 1 minus ma square. Okay. So, therefore, we find that for compressible flows the pressure gradient comprises of the frictional pressure. It has a frictional component Cf, then it has got a gravitational component, then a component due to area change, and finally, the Mach number also comes into being. Okay. So, this was just a recapitulation for your single phase compressible as well as incompressible flows. Now, in that case, let us go to the incompressible flow situation. Now, just by looking at this particular equation, this we have already derived for when just one particular fluid, an incompressible fluid, say, or even it can be a compressible, for any particular fluid we have derived this particular general equation. Now, the same equation must be applicable for two-phase flow situations. I will generally be talking about two-phase flow situations because this is the simplest kind of multi-phase flow. Okay. When we go to three-phase situations, it will just be the addition of parameters, but the basic physics more or less will remain constant. So, if we are dealing with two-phase flow, can you tell me in what ways this basic equation, how should it change, or what are the additional terms or different terms that should come, so that this particular right hand side, this gives us a representation of the actual pressure gradient which occurs under two-phase flow situations. Any idea what it should be? What are the terms that should come in this particular cases? We find that the terms which will come is, firstly there are two phases are in contact with the wall. So, therefore, instead of tau w s by A, we should have one tau w 1, just to write it down in this particular way, in order to keep it for an infinitesimal length, we can keep it ds 1 dA, or we can keep it as S 1 by A, plus there has to be a tau w 2 in this particular case. Next, if we take up the gravitational pressure component, we had a rho g sin theta in that particular case. Now, in this particular case, it has to be the rho mixture, isn't it? It has to be the effective density of the two phases. So, it has to be either rho mixture or rho T p, in whatever way you want to define it. And then there we had d d z of g u. In this particular case, there are two phases. So, there has to be g 1 u 1 plus g 2 u 2 in this particular case. Got it? So, therefore, area in this case, if you remember the original definition, the original derivation, what we took the entire area. Okay, the pressure drop, if you see the basic things which I had drawn in this particular case, you find the cross sectional area was there, the entire pressure was being applied along that particular cross sectional area. So, that area had actually come here. Okay, so, that area, so I am considering g 1 u 1 g 2 u 2 into that entire area. Okay. So, therefore, area in this case is not going to be A 1 A 2, it is being conducted over a control volume which extends over the entire cross sectional area of the pipe. Okay. So, therefore, we find that if we take this particular situation, this is just to start with, just at the first glance what appears to you. Now, if the equation it gets modified in this particular way, so we find what are the things that we need to know. We need to know tau w 1 in this particular case, we need to know tau w 2 in this particular case. Now, if we have to know tau w 1 and tau w 2, then in that case number of things we have to know. What are the things? First thing is how much of the, rather what fraction of the pipe wall is covered by fluid 1, what fraction of the pipe wall is covered by fluid 2. And we do not even know whether the relationship between tau w and your frictional factor etc., which is applicable for single phase flows, whether that is applicable for two phase flows or not. So, the first thing is there is no obvious relationship between the wall shear stress in single phase and two phase flows. The other thing which comes into, the other thing is that in this particular case, if you observe, we find that there should be interfacial shear also. So, apart from tau w 1 and tau w 2, there should be a tau I as well. Okay. For the total balance it does not come, but definitely there is a tau I. Same thing, just as you were telling, instead of 1 A is a measurable parameter. In this case we need to know A 1 and A 2. If we have to know A1, A2, we have to know what is the distribution of the two phases in the conduit. Then remember, here we have one, instead of S, the wetted perimeter, we have S1 and S2. Along with that, we have an SI as well. Okay. So, therefore, we find what are the problems which are coming up. First is no obvious relationship between wall shear stress in single and two phase flow. Information is needed about the interfacial shear stress tau I. S includes S1, S2, Si. Then A includes A1 and A2. Okay. These things are coming up. So, therefore, in order to know A1, A2, in order to know S1, S2 and things like that, first thing what we have to know is the distribution of the two phases. Now, remember one thing, this distribution is not in our hands completely. We can just control the amount of the two fluids that we can introduce in the conduit. But whatever we introduce, in the same proportion the two fluids might not flow inside the conduit. Suppose you have introduced 1 LPM of air and 1 LPM of water, or 10 LPM of air and 10 LPM of water. Okay. Now, so you know what is your inlet composition? It is 50%. You have introduced a mixture with 50% air and 50% water. Now, when it flows inside the conduit, remember both of them have different densities. So, therefore, there will be a slip effect. One particular fluid will try to slip past the other fluid, and therefore, in that case what we find is, just because of that slip, the composition of the fluids at the inlet will not be equal to the composition of the fluids in the inside the pipe. Okay. Inside the pipe there will be a slip between the phases. Just because of the slip, what happens, the lighter phase it will tend to slip past the heavier one, as a result of which the in situ composition and the inlet compositions are going to change. This is another problem in this particular case. So, therefore, unless you know the in situ composition, can you find out a proper definition or a proper expression of rho m, rho mixture? What is this rho mixture? Suppose we deal with a gas liquid mixture, and suppose we express the composition in terms of void fraction, which you have already done. Okay. So, we take alpha as the void fraction. So, what is this rho mixture? It should be alpha into rho 2, where 2, or rather alpha into rho gas, let me take it, plus 1 minus alpha into rho liquid, correct. So, in this particular case, unless you know alpha, the void fraction, you cannot proceed to do anything. This is number one. So, firstly you have to know alpha. What is alpha? This is the in situ void fraction, remember, and this is not equal to the inlet void fraction. So, this is the thing that you are supposed, in this part is your input, you can control it, you can regulate it, but this part is not within the control of any experimenter or designer. Within the control of any experimenter or designer. So, therefore, this will depend on what? This will depend upon the physical properties of the fluids, it will depend upon their flow rates, and most importantly it will depend on how they are distributed, because the slip depends on how they are distributed. For example, I will give you another example. Suppose again air water, let us take. So, in situ means inside the conduit at that particular position where you want to find out the composition. Okay. For example, suppose see this particular in situ composition, how it changes. Suppose we are having air water. Okay. So, we are having a large amount of water, a small amount of air. What do you expect when they are flowing? Air will be distributed as bubbles. We will be studying this in much more details. On the contrary, you have large amount of air, small amount of water. How will they be distributed? they will be distributed as there will be gas in the center and liquid will be flowing as films at the wall. Now, do you mean to say the slip will be same for both these cases? It cannot be same. So, it depends upon the interfacial distribution as well. Okay. So, therefore, what we find is that we had started with the single phase equation. What we did, we simply added up, it is not as simple as I tell you, but just at one go we simply tried to add up a few extra terms. Instead of tau w, we had your tau w 1 and tau w 2. Then instead of rho, naturally we are going to have rho m. So, just by these simple things what we find is that in this particular case the situation becomes much more complex as compared to single phase flows. Sorry, why it becomes much more complex? Because firstly two things, the two phases can distribute themselves in a large number of ways, and that is not within the control of the experimenter or the designer. And the other thing is there is a slip between the phases, due to which the in situ composition and the inlet compositions, they are very different. Now, due to this what happens? For single phase flow, what do you need to know? You just need to know whether the flow is in laminar or turbulent. If you do not do that, you cannot find out the frictional pressure gradient, can you? You cannot use laminar flow equations and expect to get accurate results for turbulent flow conditions. Can you do it? You have to find out whether the flow is under laminar or turbulent flow conditions. For that, what you have to do? It is a very well defined process, there is no argument about it. Go to find out the Reynolds number, refer to the Moody's plot or whatever it is and do it. Why can't you use laminar flow equations for turbulent flow? Just because the distribution is completely different. We have a very ordered type of flow in laminar flow and a very chaotic random flow for turbulent flow. Same thing in this particular case also, it is just not sufficient to know whether individual fluids are in laminar or turbulent flow, but we need to know whether the variety of distribution, we have to know the distribution of the two phases. Just like we cannot use laminar flow equations to predict turbulent flow pressure drop, in this particular case also we cannot use bubbly flow equations to predict the pressure drop of annular flow. Can we do it? Suppose we have derived equation for this particular bubbly flow case. Okay. So, for this particular bubbly flow case, suppose we have derived a equation, we cannot use the same equation to find out the pressure drop in this particular case. The total flow distribution is different. Okay. So, therefore, what we find is that we have to know firstly the distribution of the two phases, and interestingly for single phase flows what we have, whether the pipe is inclined, it is vertical, it is horizontal, it hardly matters. Okay. The same Reynolds number we use to find out whether the flow is laminar or turbulent. But interestingly in this particular case we find that the distribution, it depends upon the geometry of the conduit, whether it is circular, its size, its shape, whether it is a micro channel or it is a milli channel or it is a large channel, on that it depends. And it depends upon the orientation, whether it is vertical, whether it is horizontal, whether it is inclined. Why? Whenever it is horizontal, what happens? There is a stratification tendency, gravity acts on the two phases differently, and therefore, the lighter phase will like to stay on the top, the heavier phase on the bottom. Okay. This is not going to happen for vertical cases, agreed. So, therefore, in this particular case finding out laminar and turbulent were much easier. In this particular case we find that flow geometry becomes very important, the flow orientation becomes very important, flow direction becomes very important in the same vertical pipe, whether it is upflow or downflow, it is very important, whether it is co-current flow, counter current flow, that is becomes very important. Okay. And definitely phase flow rates and properties, it goes without saying. Phase flow rate and phase property, it is important for both single phase and two phase flow situations. In addition to this particular case, we find that we have to know the distribution of the two phases for any particular hydrodynamic study, and if we have to know the distribution of the two phases, we have to take into consideration the flow geometry, the orientation, the flow direction and so on and so forth. There is one other very interesting thing which I would like to tell you with respect to this particular situation. So, firstly we found out that to find out rho m we need to know the in situ composition or the alpha. There is another very interesting thing which I would like to show you. See, in this particular case, this acceleration pressure gradient we had expressed it as d dz of g u. What is this u? This is nothing but g by rho, isn't it? So, therefore, this can be expressed as g square 1 by rho, or in other words this can be written down as d dz of v, right. So, therefore, minus dp dz acceleration for your single phase cases, this becomes g square. It can also be written in this particular form, yes or no? We can write it in this particular form. Why could we write it? Because we could just take 1 by rho equals to v. Similar way, we can write down dp dz acceleration for two phase flow conditions as g square d dz of v mixture. All of you agree we can write this down, but here comes a catch. In single phase flow, what we could write down? We could simply write down rho equals to 1 by v. Tell me, for two phase cases, can we straight away write down, I have already put not equal to, can we straight away write down that your 1 by v m equals to rho m? We cannot write it down. Why can't we write it down? Any idea, anybody? Let us go to the basic definition of density and specific volume. What is the specific volume? It is the volume of 1 kg of the substance. Agreed? Now, when it is a single phase thing, then in that case and rho is the weight of 1 meter cube or unit volume of the substance. Do you agree? Okay, so again listen to it. Rho is the weight of unit volume of the substance, V is the volume of unit mass of the substance. Say our unit of volume is 1 meter cube SI units and this is 1 kg. Now, when we take a two phase flow situation, what happens? In 1 kg of the mixture, we have x kg vapor, where x is the quality. Remember, quality and void fraction you have already come across, and we have 1 minus x kg liquid. Agreed? So, therefore, in this particular case, what is Vm equals to x V vapor if we take, or it is better I put it gas, x V gas plus 1 minus x V liquid. Agreed? Now, if I take 1 liter mixture or say 1 meter cube of the mixture, what is has? It has alpha meter cube gas and 1 minus alpha meter cube liquid. Do you agree with me? So, therefore, what is rho T p in this particular case? It is alpha into rho gas plus 1 minus alpha into rho liquid. This rho gas is equal to 1 by V gas, rho liquid is equal to 1 by V liquid, but definitely rho Tp cannot be equal to, or rather let me make it mixture, rho m cannot be made equal to 1 by Vm. The basic definitions are completely different. Is it clear to all of you? So, therefore, what we find is, so just try to understand the complications which have been introduced here just by the introduction of an additional phase in this particular case. So, in this particular case, I would like to conclude this particular lecture by telling you that the hydrodynamics in this particular in two phase flow situations is many folds more complex as compared to single phase flow. Why? Existence of multiple deformable moving interface. Try to understand. It is a multiple deformable moving interface, particularly for gas liquid cases, multiscale physics of the flow phenomena. Next, near the interface what we find, there is a significant discontinuity of the flow property. It instantly shifts from the property of one particular phase to the other phase, and therefore, there is complicated flow field near the interface. For gas liquid, vapor liquid cases, there is the compressibility of the gas phase. Then as I was telling you, tau W1, tau W2, they may not be appropriately predicted by single phase equations, because we may have different wall interactions for the different fluids, and therefore, for all these things we find that the two phase flow situation becomes many folds more complex as compared to single phase flow conditions. And therefore, in order to study two phase flow, even if we have to make this particular equation our starting point, even for that particular case also, what we have to do? First, we have to know the distribution of the two phases. Once we can know what are the distribution of the two phases, how the two phases can be distributed, only after that, for different distributions we can find out that what can be the generalized analytical models that can be proposed. Accordingly, we will be going for the analysis of those particular, we assume a type of flow and we try to analyze that particular flow. In that, or rather in following that, we would like to propose some simple analytical models, and after that we will be taking up some flow pattern specific models. Now, before I conclude, I would like to mention the textbooks which you can take up for this particular case. The textbooks, a large number of textbooks are already available. This is wrong, this has to be Wallace, this inverted comma should not be there. Now, among this large number of textbooks which are available, what I would like to say is our library has got a number of textbooks. I will mostly be discussing from one dimensional two phase flow by G.B. Wallace. We will also be taking up certain aspects from the handbook of multiphase systems, measurement of two phase flow parameters, and maybe two phase flow in chemical engineering, two phase flow in complex systems. Okay, so, as the case may be, you please try to remember that since two phase flow it has still not become a very well prevalent textbook material till now. So, therefore, good amount of things might also be taken from different papers, from different research findings, but for the time being initially probably Wallace, Govier and Aziz, Butterworth and Hewitt, the book by Hewitt, the handbook of multiphase systems, these books will more or less suffice to do with you. Okay. So, we conclude the session today with this particular note, and from tomorrow we are going to start a discussion on the estimation of different flow patterns under different flow conditions for different fluid types. Thank you very much.